20-1s. As we near the end of chapter 6, it's time for everybody's favorites, word problems. Oh, how we love them, and we get to do them with rational equations now. Woo! All right. As always, with word problems, hopefully you've done enough work this unit that solving rational equations, you know what, it's manageable. Yeah, sometimes we make errors, but at least we know the process. Word problems, I don't think the math, if you know it, is the problem. It's setting it up. It's the setup, like so much of what we've done, that can cause us the grief. Well, what we're going to do is I'm going to split this into 2 different videos over 2 days so you're not overwhelmed quite as much. But to start off with, we are going to look at things that are referred to as distance problems, a unique situation that has a bit of a process to it, and rate of work problems. These are 2 unique situations that use rational equations to solve, but you're going to need a little bit of guidance setting it up. In the assignments, you will have a couple of questions that are just general knowledge where you need to read and interpret. Interpret also means think. So some of you might be in a bit of trouble. You're going to read and you're going to have to think and interpret in order to set it up. But the lessons that I'm going to do are going to be focused on distance problems and rate of work problems. First one we're going to do today is rate of work problems, which is page 14 of the booklet. Now, distance problems. Distance is based on the distance you travel is based on the rate or velocity you're moving times time. Well, we can manipulate that formula. We can also write an equation for just the rate of something or the time of something. Rate would be distance divided by time, whereas time would be distance divided by rate, not time. So sorry. So there's the equation, or the little equations we're going to work. Now with distance problems will always involve two velocities within a question. It might be 2 separate objects. It might be the same object moving different velocities over time. What we're going to do is identify the distance, the rate, and the time for each object and then create an equation from that. Looks a little overwhelming if you buy into this chart. This chart, if you I mean, it's not really difficult. Distance, rate, time, and then your 2 different velocities will go into it. Filling in the charts isn't that bad. And then creating the equation is where you're going to have to interpret or think a little bit. Now, just as a quick aside, distance problems, it's always the joke. 2 trains going towards each other, and you see it in all kinds of cartoons. Got to be honest with you, the cartoons where I see distance problems, they actually always have an answer. Foxtrot is one that always has been known to have some distance problems in them. Same thing with the Far Side cartoons. I have solved, not a ton, but a handful of distance problems from those cartoons using this process. It's magical where math happens. Anyways, here we go. Distance problems. Let's take a look at the first example. Jeremy biked somewhere there and back. I abbreviated these. So Jeremy went somewhere, 140 kilometers, and then he came back. What assumption are we making? We're assuming that there is 140 kilometers, back is 144 as well. Always assume the same route. He went twice as fast there. Total travel time was 27 hours. Algebraically, now that doesn't say that in the booklet, but that's the assumption, is algebraically solve his rates or his velocities. So here's our chart. We know one situation is going there and one situation is coming back. What can we fill in? Well, we know that we have 144 kilometers there and 144 kilometers back. Pretty straightforward. What else do we know? We know that he went twice as fast there. So we know the rate going there was quicker than the rate coming back. It doesn't, and it tells us that there was 27 hours. Now, what we have to be careful of is we have information, and we know that it's twice as fast there. That's an easy piece of information to put in. So for my rate, and because that's what we're solving for, because we're solving for rates, we need an unknown variable for a rate. Well, if he went twice as fast there, we could call that twice x. So coming back, he went a velocity of x, but going there, he went twice or double x. Now, there is information for the time. However, once you fill in two columns, we're going to fill in this third column using those little d equals rt, r equals d over t, and t equals d over r formulas. So time, what do we know about time? Well, time is distance divided by rate. So that's what I'm going to put into my time blocks. We know time is distance, 144, divided by a rate of 2x. That's what I could use to figure out how long it took them going there. We know there was 144 kilometers coming back, divided by the rate, which is x. So these are two expressions to represent the time there and back. Now, fill in two of the rows of our charts, use those little equations to fill in the third row. Now we need an equation. This is where the last piece of information comes in for the equation. We know it was 27 hours total travel time. So that means the time going there and together with the time coming back was 27 hours. So I can now plug in. What do we know about the time going there? Well, the time going there is described as 144 over 2x plus the time coming back. And the time coming back is described as 144 divided by x. And together, those two things should total 27. So there's what we need to do. Solve that rational equation. Lots of little steps to create the equation itself. How do I solve? Well, I want to get rid of denominators. So what we need to start with, what is the common denominator for this situation? Well, it's 2x and an x. Well, 2x and x means the common denominator would be 2x. I could multiply. Because this is a single term monomial, I need to multiply every part of my equation by the common denominator. Why? Because now I cancel. That's how we solve. Identify the common denominator. I can cancel the 2x, and we're left with 144. Here, because it's monomials, this is like a 2 and an x. I can cancel the x with the x, and I'm left with 288. And that will equal 27 times 2x. And 27 times 2x is 54x. There's my equation. Eliminated the denominator, and now I can solve. So what are we left with? Combine the like terms. Here, what do we got? 2, carry the 1, 12, 3, carry the 1. 432 equals 54x. Divide, and we get x equal to 8. So when I have x equal to 8, what does that tell me? Well, I need to go back to my chart. What did x represent? X represents the rate coming back from the trip. So we know 8 is kilometers per hour to return. There's what we're looking at. Have we answered the question? Not entirely, because we want the rates, So if the rate going was 8, well, or sorry, coming back was 8, well, the rate going would be 2x, which is 2 times 8, 16 kilometers per hour to go wherever he was going. So there you go. Lots of little steps to create the equation, but hopefully the equation's not complicated to solve. Here we go with the one underneath. Let's walk through this one again together. Jim walked 12 kilometers. He then biked 5 times faster for 100 kilometers. Total trip time was 8 hours. Algebraically solve for his walking and biking rates. That's what we're trying to find. So somewhere in these rate boxes, we need a variable. Well, what can we start with? What are the two things we're dealing with in terms of the trip, the velocities? Well, there was walk time and there was bike time. So now we want to fill that in. Do we know about the distance of the walk? It was 12 kilometers. The bike was 100 kilometers. That we know. The total trip time was 8 hours. Don't care about that right now because I'm trying to find the rate, an x for my rate. We know he biked 5 times faster than walking. So walking could be x and biking is 5 times x. So however fast he walked, he was going 5 times that on the bike. Once we have 2 rows filled in, even though we have information up here about travel time, 2 rows have been filled in. What do I know about time? Well, time is distance divided by rate. So the time walking was 12 divided by x. The time biking was distance 100 over 5x. Charts filled in. So now I go back to the question, and what's that extra piece? Well, we've already addressed it a little bit. Total trip time was 8 hours. That's information for the equation. We know that time walking plus time biking was a total of 8 hours. So I incorporate that. Time walking is 12 over x. Plus time biking is 100 over 5x. And that equals a total of 8 hours. There's your equation, rational equation that we need to solve. First thing for solving the rational equation, we have to identify a common denominator so we can multiply by it. X and 5x, 5x works nice. So I'm going to have to multiply every term of the equation, every part of that equation by the common denominator 5x. The nice one is 5x and 5x cancels, leaves us with 100. Here, x will cancel with x. 12 times 5 is 60. And here we have 8 times 5x, which is 40x. There's our new equation. How are we going to solve for x? Combine 160 equals 40x, divide both sides by 40, and x equals 4. But we have to double check, what exactly does x represent? Go to our chart. X is the rate when walking. So we know that x is 4 kilometers per hour walking. And 5x is the velocity on the bike, because that's what it tells us. So 5 times the x value of 4 is 20 kilometers per hour biking. And now we've solved the question. The chart gets filled in, then we need to create the equation using the information from the charts. All right, here's another one. I suggest maybe on page 15, give it a try on your own, and then we'll do it together, but I suggest first try it on your own, see what you come up with. Here we go. Sheldon and Simon are leaving Sherwood Park in opposite directions. So what are the two things? We're dealing with Simon and we're dealing with Sheldon. There's what I can fill in. We know that they were leaving in opposite directions and Simon was traveling 18 kilometers per hour faster. Well, if Simon was going faster, I like working with positives, so I'm going to go Simon was X plus 18 and Sheldon was X. We don't know either one, but one will be X, one will be X plus 18. What else do we know? We know in 6 hours they are 972 kilometers apart. So do we know the distance that Simon or Sheldon traveled? No, because what's happening here is they're in Sherwood Park. One's going one direction and one's going the other. They're going to be 972 apart total. So we're not sure exactly what each of them is. That doesn't help us. But we do know that in 6 hours. So when they leave, we're going to assume that they're leaving at the same time. So we can assume they've both traveled for 6 hours. Simon going faster. So we know Simon is going to have traveled further because in the same amount of time, he'll have gone further. But we're still not sure yet what each of them is. But once we have two pieces of information, we fill in the chart using the little formula. What do we know about distance? Well, distance is rate times time. So this time, what do I put into this box? Well, distance will be 6 hours at X plus 18 kilometers per hour. That's how far Simon will have traveled. How far will Sheldon have traveled? 6 hours at X kilometers per hour. Our chart's filled in. What's the piece of information we haven't actually used in the chart yet? It's this 972. 972 is each individual totaled together. So what does this tell us? This tells us the distance that Simon went plus the distance that Sheldon went will equal 972. There's our equation. How far did Simon go? We're not sure, but we've called it 6 times X plus 18. How far did Sheldon go? We don't know, but we've called it 6 times X. And that has to equal 672. So there's what we're looking at for an equation. Distribute and then combine like terms. 6x plus 108 plus 6x equals 972. Combine like terms. 12x plus 108 equals 972. At that point, you can solve for x, subtract 108, divide by 12, and x is 72 kilometers per hour. Kind of nice with this one. It's a distance problem, but it didn't actually end up being a rational. So we didn't even have to eliminate a denominator. But what does the x represent? We always want to go back. Here's x in our chart. It represents Sheldon's travel speed. So we know Sheldon is going 72 kilometers per hour. That's Sheldon. And therefore, x plus 18, 72 plus 18, is 90 kilometers per hour for Simon. But have we answered the question? The question is, what distance did each travel? Well, we need to finish off the distance traveled. Well, Sheldon was 6 hours at 72 kilometers per hour, which works out to be 400 and, what is that? 2, carry the 1, 432 kilometers. And Simon, for 6 hours, went 90 kilometers per hour, which works out to be 540 kilometers. That's what the question's asked for. Always make sure you've answered the question. We didn't have a rational, but we have to make sure that what we solve for isn't necessarily what the question asked for. What's great about this is if I do add their two distances, they're 972 kilometers apart, which is what they should have been. So there's our solution. Last one, and then you can get to work. One more distance problem. Page 15, let's take a look at that one. Give it a try on your own, and then we'll talk. All right, hopefully you've given it a try on your own. Let's see what we got. John went from A to B in 8 hours. Rate returning was 15 kilometers per hour faster on the way back. So, what do we know? Well, what are the two things we're doing? We're going from A to B, and then we're going from B to A because it talks about returning. So he goes from A to B in 8 hours. So how does that help us? Is there anything else we can put in there about that? Well, I apologize. My little summary here isn't the same that's in the booklet. It says that John goes from A to B, in 10 hours, and from B to A in 8 hours. So that's kind of important. So from A to B, we know the time was 10 hours. And from B to A, we know it was 8 hours. So that's important. It also says the rate returning was faster when he was coming back. So coming back, B to A, not B to B, but B to A, coming back was faster. So X plus 15 kilometers per hour. That makes sense. Coming back took less time than going because he was going faster. So there's our X. Stop. We have 2 rows filled in. Let's fill in the last row. What do we know about the distance? Well, distance is rate times time. So rate times time, distance from A to B is 10x, and the distance from B to A is 8 times x plus 15. Now, this one's a little tricky in setting up the equation because we've used all the information from the equation. The 10 hours, the 8 hours, the 15 kilometers per hour faster. There's nothing else in this question that allows us to set up an equation, and I can't use the same piece of information twice. Can anyone think of something that's important for this? Well, what do we know about going from A to B and B to A? Well, we know that the distance going is going to be the same as the distance returning. Or maybe did they take a different route? Our assumption is not. So we know the distance going has been identified as 10x, and we know the distance returning has been identified as 8 times x plus 15. So distance equals distance. Doesn't outright state it, but the whole question talks about it. So now we solve. 10x is equal to 8x plus 120. Subtract 8x, get x's to one side. 2x is 120, and x works out to be 60. So x works out to be 60, but what exactly is 60? X is 60, which is the rate going. So it's 60 kilometers per hour going to B, and then we have the x plus 15, which would be 75 kilometers per hour returning. So there's our x and our x plus 15 value. Have we answered the question? We have not. The question says, how far is it from A to B? So we want distance. Well, distance from A to B can be described as 10 times x, which we now know is 60, because that's what the distance going is. 10 times 60, 600 kilometers. Well, let's do a quick check, because what should the distance returning be? It should be the same thing, and we know the distance returning is 8 hours at 75 kilometers per hour, and when you multiply that, you get 600 kilometers. which is good because it doesn't matter whether you're going or returning. You're going the same distance, which is 600 kilometers. So distance problems. A little tricky in the setup, but it's very routine. If you practice it, it kind of works. So, booklet, page 16 has 2 more questions. Remember, I have given you my answer booklet. You can check your answers. Textbook, 2 questions out of there that are good questions. Then in the worksheet section of the Google Classroom, there is a word problem worksheet. Number 1 to 5, more distance problem practice. Distance problems, distance problems, distance problems. That's what your focus is. Practice it because it becomes easier the more you do it. Have fun with it.